and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue to learn about linear models and we'll look at the implementation of RidgeCV, RidgeClassifier, and RidgeClassifierCV. If you remember in the previous video, we talked about L2 regularization using Ridge. In this video, we'll look at the implementation, and this is the plot from the previous video. Here, a few things I want to clarify. One is that the train MSE is 0.16 for alpha is equal to 0.01, and the train MSE for alpha is equal to 1.0 is 0.30, as we shall see now once we run this code. Additionally, the plots here, the blue dots show the original data, which is just one feature X. However, the model is fitted on a polynomial data set. So we convert that data set with just one feature into 20 features, and we are fitting the model on 20 features because it's easier to show overfitting when the number of features are larger and the number of samples, number of rows are lesser. So the plot here actually is not the correct way to show the fit, because to correctly show the fit, we would have to plot all the 20 dimensional features in one plot and then show that here this is only for illustration purpose to show how the fit can vary when we increase the alpha value on based on the original data set that's in the background. It's just to reiterate that if you have 20 features, then you cannot plot just one feature of that with a predicted curve as shown in this plot. This is just for illustration purposes. Jupyter Notebook, I've imported these libraries: preprocessing, datasets, linear model, test split, matrix, and matplotlib. And for versions, these are the versions I'm using. Now for data, we are going to use the create a random data as shown here, and I'm using the sin function to give it a wave type of shape. And finally, because we are trying to explain ridge regression and overfitting, we need to create some additional features rather than using just one feature. I'm using the polynomial features to create more features, and we have the degrees set to 20, and we have 50 samples. So we create that here, and we also have the same way we create the test set that is shown below. And those are the shapes of the data set we have. Now the first item that we'll try is linear regression. And for linear regression, we have already seen this. We are going to create the parameter reg and then use linear underscore model dot linear regression, and once this is initialized, we can use that for fitting, and we can fit it on xp because that's the x dataset, train dataset with more features. And we can use, after fitting, we can use that to calculate the predicted value. So y underscore pred underscore train is equal to reg dot predict, and this is based on the train set. And then we have y underscore pred underscore test is equal to reg dot predict, and this is on the test data set. So once we have these, we can go ahead and print those values. So let's do that. Print, and here we can specify linear MSE, and this is for the train set, is equal to matrix dot mean underscore squared underscore error, and here we specify y underscore train, y underscore pred underscore train, and let me copy this, paste it here. We have test, and again we are going to use the y test right here. So this is the MSE, these are the MSE values that we get. We can see that the model fits very well on the train set and does poorly on the test set, and that's a good example of overfitting. Now let's try to create a similar effect using the ridge when we set the value of alpha to 0. So for this, what I'm going to do is create right here. So solver is equal to, we'll use the solver svd, and for ridge regression, the first variable will you create is reg underscore ridge 1, and the reason is because we are going to try several alpha values. Linear underscore model dot ridge, and here we'll set the alpha to 0 and solver to solver that we have specified above, and then we'll use that to fit. So our ridge1 dot fit, and this would be fit on the train set. And once we have done that, we can, I'm going to copy most of, because we'll be using the same line of code. So here instead of this, we'll specify ridge1, because this is for the ridge model, ridge1, and we predict based on that. And here this would be again ridge1, because that's what we initialized here. So we change that ridge1. So now we have the predicted values for the train and test set using the ridge method with the alpha value of 0. Let's go ahead and print this out. So ridge MSC for train and the ridge MSC for test. And again, in this particular place, we have the y train, which is good. What we need to do is change this part, and I'm going to copy and paste all of these right here. So now if we run this, we get the similar results. We have the train MSC is much lower, close to 0. However, the test image is much higher. It's 118.9, so about 119. Now let's copy this and see if we can do better. So I'm going to change the value of alpha to 0.01, and let's call this ridge2 instead of ridge1. So when we do the plotting, we have these data available. So this was with alpha of, let's specify alpha here as well. So alpha is equal to 0, and this again is alpha is equal to 0. Now this would be alpha is equal to 0.01, and again this would be the same, alpha is equal to 0.01. Now the next part is we need to change the 2 here, 1 to 2 in all these cases. So we are we are initializing ridge2 with alpha value of 0.01, and then fitting that on the train set, and then predicting using ridge2 on the train data and then on the test data, saving in these two, and that's what we are printing out. And as you can see, we have significantly reduced the MAC for test set, which is really good. Now moving on, let's use another alpha value. So we'll specify this as the ridge 3, and here we'll use the alpha value of 1.0, and again we'll change these all 2's to 3's right here, and this will be 1.0, and similarly this also will be 1.0, and finally we have for the predicted, this would be 3. So when we run this, we get alpha value of sorry, this should be equal to, and here we can see that we get a ridge MSC is 0.3, and we get test value of 0.37. Now these are the corrected values. We have train MSC of 0.16, and the train MSC for when alpha is 1, it's 0.30, and we can see the test MAC has considerably increased in case of alpha when 0.10 as compared to alpha of 0.01. Now, another point I want to mention here is that the plots are we did the fit on polynomial data set with 20 features. So it's a 20-dimensional data set, and we are plotting just one one of those columns, one feature, and we are looking at the fit for one of the features. So that's not the accurate way. That's actually not the correct way of plotting the data, because we are not plotting on the other 19 features in here. However, for just for illustration purposes, to show the changes in the type of fit for the line, we can see that we increasing the alpha, we can reduce the amount of overfitting. So just to visualize that, I've added these slides in here. Now let's see how we can plot these. So figure, will create subplots. So figure is equal to plt dot figure, and we'll set the fig size is equal to 20 by 4. Then we'll specify the rows and columns. So R and C is equal to 1 comma 4. Now the first subplot we'll create is for linear regression, and this is RC, and that's the number first plot. plt dot scatter, and here we have x test, y test, and alpha is equal to, this is a different alpha, this is just for transparency, it has nothing to do with regularization. And we plot the line with plt dot plot x test y underscore pred underscore test, and we are plotting only the test data in this case, not the train data. Label is equal to linear and regression, so that's the label for the first one. And let's see how this works. This should be a tuple. Okay, and we can fix that. So we need to limit the x and y axis. So plt dot x lim is, let's go from 0 to 1.1, and then plt dot y limit, we can go from -2 to 2, and let's and that fixes that part. Now we can label this. So plt dot x label, we have feature x. So this is actual, we are saying at we are just plotting in 2 dimensions. Actually there are more features on which we fitted the polynomial model, but here we are plotting only one y label, because the fit eventually is on the original data set. So y, and this we can give it a title, plt dot title linear regression, and this is without regularization. So that's the plot we have. Now we can simply copy this over and over and just change a couple of values. So for the second plot, we have the background data is the same. What changes is this, which is where we are using the y underscore pred underscore ridge1, and we'll change the color to green, and then label would be ridge, and this is alpha value of 0. Everything else stays the same. This becomes the ridge, and again this is without alpha, without regularization, so I'll leave that as is. So we have this ridge underscore 1 is not defined. Aha, and that's because we have the train and test specified. So this should be test. So that's the second plot right there, and it's similar to the what we had before. Now after this we have the remaining 2 plots, so 3 and 4. For these we are going to use the prediction from the 2 and 3, reach 2, reach 3 that we created, and this would be 1.0 and this would be 0.01. And let's give these colors blue and give this color gray. Now the rest, everything stays the same. This is with regularization, this is again with regularization, and again here the alpha values would be different, so we can specify those. So here let's say alpha is equal to 0.01. Here we have on the new line alpha is equal to 1.0, and I'm going to copy this and paste it right here. We have alpha of 0.0. Now when we run this, we get this plot that we saw in the previous video, where the first two plots show overfitting and then the remaining two plots show data which is not overfitting. Now let's also see how we can get the coefficients. So let's print these out. Print uh, no regularization, and the coefficients for that would be in reg.coef. So the very first one that we fitted, so this is the model that we have, so we need the coefficients for that, and we get the coefficients by this, and these are the coefficients. We'll print them in a better way. So let's reshape this, reshape -1 and let's round it off to 2 decimals. So okay, so those are the coefficients we have, and we can see these are much larger values. So this should be round dot 2. Okay, these are much higher values, and similarly we can print the coefficients for others as well. So print alpha. So the first one is alpha is equal to 0, and this is for ridge, and the coefficients would be in the model regularization, or reg underscore ridge 1.coef, and then these can stay the same. So we have these as well. As you can see, these are the same as what we had before. Now if we plot for the values of 0.01 and 1.0, let's see how those coefficients look. And here, as you can see, for 0.01 they are much smaller than these, and then again for 1 they are again much smaller. So right here, so these are going closer to 0. Most of them are less than 1. These are, some of them are greater than 1. So that was for what the ridge can do. And now let's look at how we can use RidgeCV and see if it helps us improve the mean squared error. So here we are going to look at RidgeCV, and for this comparison we'll also do the linear regression again. Now first item we'll do is import the dataset. So we'll save it in the variable Boston. So datasets dot load underscore Boston, and we'll create the train and test set, the x train x test, y underscore train y underscore test, and here we'll use the train underscore test underscore split, and the data dot target, and that's the data is not defined, and that's because this is Boston. So sorry about that. Boston and Boston. Okay, so if we were to look at this, it's a big dictionary with the keys data, target, feature names, and description. So what we are doing with the Boston.data is we are getting just the data part of it, And if you look at this shape, it's this matrix, and again for target, it is this matrix. Finally, we can also look at the description. So DSCR, if you type that, it comes in this format, but to make it more legible, we can print it. So here we have 13 features and one target. So these are the features, and then the median value is the final target. So let's see how we can use this. The first item that we'll do is we'll set a random seed. So random dot seed of 0, and then we have already loaded the data set. So the first item we'll do is linear regression. So reg underscore linear is equal to linear underscore model dot linear regression, and normalize is equal to true. We'll set that. Now we'll fit it. So linear dot fit, and this would be fit to x train, y underscore train, and finally we can predict. So y underscore predict linear, and this time we'll predict only on the test set. So reg underscore linear underscore dot predict, and we predict on the test set reg underscore test, and let's go ahead and print the output. So linear MSE, and this of course has no alpha value. Metrics, so we can calculate the metric mean squared error. So mean underscore squared underscore error, and here we can specify the y underscore test and specify y underscore pred underscore linear. So that is the value we have for the MSE. Similar to this, we can go ahead and create the next one, which is using just ridge. So let's use ridge, and for that we just need to specify ridge, and we'll specify alpha value of 0.5. Now this is going to be ridge, and again this is going to be ridge. We fit the ridge with alpha value of 0.5 and save it in the regularization ridge, and fit it on the train set, predict on the train set using the ridge, and here we have the predicted value saved in y underscore pred underscore ridge. So this is the MAC for the ridge, and again this is MAC for ridge. So we get output value that is in this case higher than what we have for the linear case up above. Now let's copy this and paste it here. Now we'll use the RidgeCV, and for RidgeCV we just need to change this model to RidgeCV, and I'll change the variable names also to RidgeCV as seen here. So now when we run this is RidgeCV. I think we have an error. Keyword alpha value unexpected, right? So what we can specify with the RidgeCV is alpha values. So we can specify, let's say 0.001, 0.01, 0.1, 0. Or let's say 1.0, and when we run this now, we see that using in this example, we see that with cross validation we were able to reduce the MSE to 10.6 as compared to using just ridge with alpha value of 0.5, and it is slightly better than just the linear MSE that we have up above. So what RidgeCV does is it check through all these values. We can specify even more number of alphas and see if we can improve the MSE even better. So that's how the RidgeCV works. Now let's look at how we can use RidgeClassifier. RidgeClassifier, and we'll also use the RidgeClassifierCV. So both methods. Now for this, we'll use the dataset breast cancer dataset. So we'll save that here. Data is equal to datasets dot load underscore breast underscore cancer. And uh, if we want to take a look at the description, let's print this. So this is the data we have. We have 569 rows and we have 30 numeric columns, and, and there is one target column which is class whether the cancer is malignant or benign, and we'll use that data set. So we can also look at the data shape is 569, and then look at the target shape. So it's 569. So target would be just data dot target should be just ones and zeros, as we can see. Okay. So first item, same as before, we'll split the data set. So x train, y, x train, x test, and then y train, y underscore train, and y underscore test. And then we are going to train underscore test underscore split, and here we specify data dot data, data dot target, and okay, so that should work. And we can even look at the size. So we look at x underscore train dot shape, we have 462 samples in train set, and x underscore test dot shape, we have around 143 rows or samples in the test dataset. So let's first try using RidgeClassifier only. So RidgeClassifier, and for this we'll create a variable clf underscore rc linear underscore model dot RidgeClassifier, and you can fit this clf underscore rc dot fit, and this would be on the train set, x underscore train, y underscore train, and we can print the output. So the first is train. We'll print the score on both train and test score. So this is only RidgeClassifier without the cross validation part. So clf underscore rc dot score, and this would be on the x underscore train, y underscore train, and I'm going to go ahead and copy paste this again. So the second one is on the test, so test, and this is x test, y test. So when we run this, this is the score we get. The higher score, the better it is. So we can see that score is about 0.95 using RidgeClassifier. Now if we use RidgeClassifierCV, let's see if we can improve this. So I'm just going to substitute this RidgeClassifier with RidgeClassifierCV, and here we can specify the values of alpha. So 0.001, 0.01, 0.1, and 1 with this, and let's add CV here. So this is RidgeClassifierCV. So I'm going to add the letter V right here, and this is RCV, and this would be RidgeClassifier with validation. Now when we run this, we get an output which is surprisingly similar. The test score is similar to what we had before, which is 0.958. However, we can see that the the train score has changed. So this accuracy can also be increased further if you do normalization, and also change, also look at other parameters that can be changed with Ridge classifier. In also in Ridge regression that we did earlier, there are categorical variables. Those could be uh, changed to one hot encoding. We did not do any of that. So uh, you could try working through this example again and try to see if you can increase the final accuracy or the MSC of the models that we tried even better than what we had in this video. I hope in this video and the previous video you learned what is Ridge and how to implement different variations of Ridge regression and Ridge classifier, and also have an intuition in the background as to why we need to use ridge or regularization. And the primary takeaway message is to reduce overfitting of the data so that model generalizes well on unseen dataset such as the test dataset. We'll continue this discussion with lasso regression in the next video. Until then, please like, share, and subscribe. I hope to see you all in next video. Thank you.